What we wanted to do is explain the architecture and especially some of the more unique attributes in Nuclio. Our intention is not necessarily to look at it as a holistic solution, but some of the components that we'll discuss could actually be reused by others, or we can sort of try and absorb other components from other projects. So it's important to understand some of the modeling that we've done. We can try and propose some of those common APIs that we've developed internally as a baseline for some of the things that we're trying to discuss in the working group. I'll start with sort of a very high level architecture of what Nuclio is. So essentially what we started doing that, we had a previous version which was proprietary. And then about a year ago, we decided to open source it and sort of rewrote the entire code. And in order to make it more open to other data sources, event sources, and be more modular for future use cases. What's some essential things in the architecture? It's a real-time system. It has sort of notions of zero copy, zero context switches, no garbage cleaning, all those aspects that come from real-time. This is why its performance is so high. We did want to address all the aspects of lifecycle, so versioning. How do we test in one place and deploy in another place, because we have a lot of IoT use cases. We wanted the data and event sources to be pluggable without impacting the function, because we use functions, for example, to do backup jobs in our systems. I want to just plug the right data set that I want to back up as a parameter. I don't want to rewrite my application. Same for events. We want to trigger the same function, sometimes for testing from an HTTP event and sometimes from a stream or a message queue. And the general idea is that it needs to be portable, pretty much like with the Amazon Lambda. You can do Greengrass, you could do Snowball Edge, you could do in the cloud. So here it's even a bit more modular because you can run it on a laptop, on a Raspberry Pi, on many other platforms. So that was our requirements for the system. It's divided to, so the main component is the processor, which is the thing that wraps the function. I'll dive a bit more into it. This processor is wrapped by, on one side, something called event listener, which intercepts the events from the different types of data sources. And then you have a notion of data binding, which is the thing that binds with the different data types, like databases, stream, etc. On the control layer, we have several components. It's not necessarily bound to Kubernetes, but when it's the current implementation of controller is over Kubernetes, it could be, this is, I think, the only component that is tied to the underlying platform. There's another component, which is the builder function, also runs in a container and builds the artifacts. There's something called dealer, which I'll explain. It's a thing that allows the dynamic association between various things like jobs and shards and tasks and functions. And there's also aspects of user interface. One is a CLI, the other one is pretty much like a Go playground, and we'll see how it works. So that's the general architecture. If we dive further into the processing engine, so the event listener, you essentially implement a sort of a class that implements the event listener. There are four types of event listeners because they define the behavior of the entire workflow. And then under a class, you have different implementations. So if you go through the code, you'll see that there's like synchronous, asynchronous, stream, and polling implementations, or so we're probably gonna generalize it as batch jobs, the polling one. And under those, there are different transport implementations. Because synchronous is like a request and reply, has one behavior. Asynchronous is sort of independent set of asynchronous messages and things that we discussed. Streaming is sort of a continuous stream of messages with ordering and potentially sharded. So those are the plugins. They're implemented in a way that you can actually have zero copy all the way and zero context switches all the way from the event source to the function. And the other side, you have the data bindings. We still need to do some more work on that. So currently, sure, the Amazon APIs and our v3.io is supported, but in a few weeks, we'll add all the rest of the things in the list here. This processing runtime have abstraction of the interface to the platform. So this is why it can run over different platforms. So all the things around logging and and runtime have abstract interfaces, which if the group wants, we can start and standardize them. And I'll touch on some of them, especially like logging and others. And the function itself runs in the runtime engine if it's because all the infrastructure is designed around Golang. So if it's Golang, it's sort of inline Go routines. If it's other languages, then it's there are a few invocation mechanisms. One is like a bash, the other one is like a Unix sockets, and there's also going to be a shared memory implementation. So it's not like some of the platforms where it's like CGI that you invoke the process. The process or the workers are kept live, and then you sort of just inject the message and get events and other responses from the function. And also another unique thing is that the function we have multiple workers on a single process, and this allows us to get very high concurrency and also enable this very high performance. Okay, so if, for example, you're driving the function with HTTP requests, and those HTTP requests are blocking on I/O or something, then we'll actually be launch multiple workers concurrently to deal with all the remaining requests.
I have a question here. Sorry to interrupt. So when your event comes, the event listeners get the event. So are you going to have that function workers running there all the time, or you are going to at that time instantiate a function? A compute resource to host that function worker?
So what you're seeing here, the function processor is a process. Okay, it is live. The orchestration layer needs to decide if it needs to be live. And if, for example, this is in the doc, we refer to something called starter. So if the function is down, someone else intercepts the HTTP request, loads the process, and then ships the message into the process. In case of message queues, it's slightly different. But the idea that the process already has the runtime worm. You don't necessarily have to have all the workers up. You could sort of have 0 workers, so consume less memory if you want, and then start building the workers dynamically as the workload arrives.
Oh, so basically you have a warm compute resource there.
Yeah, but it doesn't have to be alive. It could be taken down.
Yeah, right. But for the first event, right? You have to cold start, right?
Yeah, if you're doing a cold start, then something else will intercept the event and would sort of launch. Tell the controller to launch the process.
The idea is that you could have both. You can have a configuration of a cold start or a warm start, depending on your function. YAML.
We have in the presentation also the YAML definition and the CLI definition. You can see that there is a minimum and maximum replica definition. So minimum could be 0 or could be higher number in order to preserve SLA. So that's the, yeah.
Sorry, go ahead.
So that's on this. So we discussed all those different certain implementations of models. Sorry.
Sorry, I still have a question. You just mentioned, I think say it could be either cold or warm. Is that configurable?
Yes, yes, and you could even decide how warm you want, how many instances needs to be up.
So you leave that to the user to configure it. It's not that your system automatically decide.
No, because what we see is sometimes we deal with low latency use cases where people would prefer to pay some more for the resources and launch and have sort of a 0 latency. And we've seen latencies of sort of 0.1 millisecond on the system on invocation, and so. We don't want to add another 100 or a few hundreds of milliseconds in some cases to the invocation.
Okay. Yeah, but so are you then, because you already have...
But let's, Karen, because we don't have a lot of time, let's table some of the discussion, some of the questions to the end, okay? So one unique element that we've, initially we started working with like stateful sets in order to deal with the sharding challenge of how do you distribute multiple shards to multiple functions. And eventually we decided to have something which is more dynamic. It's called the dealer. Essentially what you do, you submit the job and you tell the job how many tasks. And tasks could be very different things. Could be a number of active shards. It could be if you're, sometimes serverless doesn't feed batch jobs. Let's assume you want to do ETL. ETL is too long for a serverless function. So you may want to break the table to 1,000 smaller slices. Each one of those will run independently and checkpoint. So if you fail, you sort of start from the same point. So general idea is that you break a job into a bunch of tasks, as many as you want. There are all sorts of metadata things like, how many tasks can a process do concurrently, etc. And the dealer deals with sort of dynamically distributing the shards or the job tasks among the actual functions. Every time there is something is restarting, it will reallocate. It's actually not really working from the definition of what's up and down. It's looking at the deployment expected number, because what happens if you have a pod that just restarted, you don't want to redistribute all the shards, and then a second after that the pod went up and you redistribute again. So we watch the both events of up-down events as well as deployment scale change events. Okay, so that's a very generic mechanism. It's actually not tied to Nuclio, so we can use it even in other microservices. Okay, any questions on that?
I have a question on this. So when you say the job you divide it into tasks, are those tasks the same task or running in parallel, or they are different tasks?
So they could run in parallel depending on the metadata. You see maximum task per process or and min-max processes and all those parameters, or they could run in sort of a cascading, like I have 1,000 tasks and I'm limited to only 4 processes. So essentially I can give every process like 5 tasks. They finish 2, they get another 2, etc. Okay, so but the general idea is that we have, for every task there is a single worker thread or worker routine, not a process. So, and that maintains also the checkpointing of that stream or task or all those things.
So those tasks could perform different work, right?
Yeah, you can essentially run the same function with multiple jobs and each one with multiple tasks. But again, I think we can have an entire hour just about the sort of the dealer architecture. So let's just leave it at that. One of the use cases that we demonstrate this week at Strata is that by having serverless functions that first are so fast and real time and have those native data bindings to data, and have this sort of ability to go beyond just sort of a simple event driven to also sharding and stream processing and batch jobs, then essentially it can replace almost anything in the setup. So this is a traditional pipeline that we work with customers. You get feeds from whether it's operational databases like ETL or CDC or stream. You do all the pre-processing on those streams, like denormalization, aggregation, prediction for machine learning against a data source. You could do all the complex event processing with those. You could do all the data movement, from one repository to the cloud and back. You could do even the APIs that serve the dashboards. And essentially, you also have other services in our platform that deal with like machine learning or Spark or other things, which are, those will be sort of continuous services that have their own, APIs and TCP ports, etc. So now this approach of advancing the serverless to a broader scope helps us to use it in sort of almost any place. Okay. And this is one example that I'll show in a minute, that how we essentially take an event, do parallel enrichment across multiple tables, do complex event processing, work against like 4 different streams and tables and geomaps, 60 lines of code, all of that example. I won't dive into the next few slides. It will be something that you could look at after. This is the definition of the job spec, and there are different points into the sort of unique aspects of things like data binding. You can notice it's a Kubernetes CRD. So essentially you can do kubectl create of a bunch of things and functions in the same command. There is this definition of events that are shipped into the function. This is also something worth discussing, because this is part of how we see generalizing the event structure across multiple forms of events. This is the logging interface. We also suggest to sort of standardize the logging interface. Today we have different implementations for the logging interface, like print to the screen, pass it through HTTP, write to a file, push it to an event stream. This is another thing that I wouldn't like to have us maintaining everything. And if we can form a generalized model here and everyone agrees to it, then we can have people creating sort of plugins for logging, for stream logging, and one uniform interface. And there's also other things like the generalized data binding APIs and others. You could always overwrite it. So with that, I'll move to the demo. Eran, can you, I don't know how I'll pass you.
Sure.
Any questions until sort of Eran gets organized?
So
we have about 5 more minutes. You're on.
Okay, we'll try and rush it.
Thank you.
And by the way, we're really open to, if you think things in our model are not, we haven't done a good job, then we're open to change code and change models. Okay, so good. So Eran will show us a model, will show us the demo. One of the things that I mentioned that Nuclio comes with a built-in sort of a playground, pretty powerful. So it's essentially Kubernetes deployment. You just launch it and it works standalone. You could launch as many as you want in parallel. And what so Eran, let's start with show a simple Python. So you could see you write the function, a simple Python, you get invoked by the event and the context. The context also gets you the logging. The logging is both structured and has different levels. And then you just compile the function, run it from the same playground. You can actually also invoke it, and you could see that the return response could be either structured or unstructured. If instead of putting a structured response, I'll just put a string, it will also respond. You just won't have the flexibility to control all those things like return status, etc. And with the logging level, you can actually control in real time what kind of log messages are going to be shown to the user or be written to the log stream. Okay, so if I have a same function with different levels of logging, and I happen to run into a challenge, I'll just sort of turn on debugging and run. Okay, so that's around that. Maybe let's show a different function now in Go. Okay, and this you could see again also all the notion of logging, structures, status, etc. And maybe you can show us the performance, Eran?
Sure.
So what you'll see in Nuclio is also integrated with Prometheus, and we have our own tool for HTTP benchmarking. It's a pretty fast tool, generates about 800,000 HTTP requests per second. It's open source. And what you can see while we're running the function, we can run Prometheus, and also look at the HTTP Blaster event, and you'll see the results, hopefully.
Yeah, we're running an empty function that just returns nothing.
Okay.
Yeah, so it's just running, and Prometheus is going to update in a second.
Okay. So what you could see is that a single process currently running about 400,000 events per second. That's probably faster than anyone writing his own function, because usually developers don't have the time to deal with all those low-level optimizations. Okay, so that's around that. Maybe around, can you show us also how you invoke same function from different sources?
Yeah.
So as we mentioned, the same function signature is exactly the same across multiple types of sources. You can subclass it and extend stuff, but it's pretty comprehensive. So the nice thing is I can take the same function that I just invoked with HTTP and now invoke it through RabbitMQ. Okay, because I ask the function to listen on both asynchronous and synchronous data. I can do exactly the same from Kafka or NATS or Kinesis or RV3IO. Okay, so what Eran did is a function that sort of the RabbitMQ writes to something, and then sort of in HTTP, just to show you that it happened, is reading the content. So just to prove that it was actually running.
Yeah.
Okay, so that's on this. Maybe Eran can show us also the more comprehensive Go test. So until now, we sort of just played with sort of stuff, but you can see that I mentioned to you this real-time IoT demo that intercepts car messages and does real-time enrichment with other data sets. This is the code. You can see the first line is the data binding. We're actually having in the definition language, we're saying DB0 equals to a certain data type, certain security credentials, etc. And then that already is sort of bound to my context. And what I do here is we also have sort of like pandas or data frame, Spark data frame implementation similar to that in Python, in Go, sorry, for real time. It's also going to be open source. And you could see that what I'm doing here, I'm doing parallel read from 4 different tables, cars, drivers, road information, doing all sorts of decision making underneath, and to update geomaps, to update car driver violation streams, all that stuff. The last line, by the way, you could see that it sort of waits for completion because everything here happens asynchronously. All those 5 different updates to 5 different streams and tables happens concurrently. So that's why the last row is essentially like waiting for all those things to complete. So you could see that very few lines of code, I managed to do something that in traditional stream processing will take multiple components and won't be as elastic. And this is an elastic function. I could test it with HTTP and then drive it into a production stream using Kinesis or Kafka or anything else. So that's and that. Maybe we'll have a few minutes. Just let's show the CLI because I want to show also its pretty comprehensive features around versioning. So I hope we have 2 more minutes for that. So just show us, so there is a full-blown CLI. You could see there are so many options when you want to invoke a function. You could decide where do you want to have the repository. So, think like IoT use cases, you deploy and run a function, create an artifact, and then you want to spread the same artifact to multiple edge devices. You could do that. You could just go through the functions and you could have labels on functions, and you could do select by labels. You have versioning. You could do logging. As I mentioned, the logging level, you can control it, execute functions with different logging levels. Maybe show us the publishing feature for the versioning.
Just did.
Oh, okay. So the nice idea is that let's assume I tested the function, everything is cool. I want to now label it and tag it. So that's the publishing feature. And what I'll do with the event source, I will define which sort of label selector or which version or alias I want the event to drive. So now I could have event source, a stream that's the production stream and matches with the production function. And in parallel, I'll have a different function just for testing, and I'll invoke it with HTTP or another stream. Okay, so that's the general idea. You can update a bunch of things to each one of the versions, like environment variables. You could label functions and all those things. So it's very comprehensive. We'll probably won't have time to get into all of those things.